So we're going to start on 6.2, which is the disc washer method. Normally I have this longer intro that I would show you guys in person where we would kind of build everything together from scratch, talk about volume by slicing and everything like that. But it's a lot harder for me to teach it without being able to see your face and see how where I need to go from each step. So what I'm going to do is I'm just going to try to do something straightforward and just try to walk you through the formula and how it came to be. Again, it'll be a little bit harder because I normally use like objects in my hands a lot to explain this topic, but let's see how it goes. So suppose we have this little curve, y equals f of x, okay? And we're going to take the area under this curve, right? So we have the area under this curve. So we've been doing this for a while now. So let's say we take this area under this curve and then we spin it around the x-axis. So that means that we're going to get, you know what, let's do this guy. So that means we're going to get like this shape. Right? And then we're going to have this other side of it, and it's spun. Remember, this whole thing is spun. So this is no longer some just curve. This is an actual solid. Kind of reminds me of sometimes I get, you know, baby showers and at weddings maybe or things like that. They make these little like almost like snowflake things that you cut in pieces and then you unfold them and wrap them in a circle around something. Or like imagine a slinky. If you took a slinky and it was pretend it was solid and you just made a circle with it. That one would actually have a hole in the middle, but you get the idea that you're trying to create a solid. Now, this is going to be like some kind of bell-like shape. It almost looks like a bell, right? But it's solid all the way through. It's not hollow like a bell. This is solid all the way through. So what the disc washer method does is it's going to help us find volume by integrating area, okay? So the actual problems themselves in general are pretty easy, pretty nice. But the idea of where it came from requires a little bit of work on our part. Okay, so what I'm going to do is I'm going to draw a little rectangle right in here, a little slice. I'm going to cut out a slice of this right here. Okay, and I'm going to say that this distance from here to here is big R. Let's call that distance R. Now, why did I choose R? Well, whenever you rotate something like this, you're technically creating circles, right? Everything's based on 360 degrees of rotation, or 2 pi or 1 revolution, however you want to say it. So we're technically building a circle. Okay, so if you took a ruler and you spun the ruler around a fixed point, and everywhere that ruler touched, it became solid, you would have something that looks like a disc. Okay, so that's why this is called the disc washer method. This is used for rotating curves around the X or the Y axis. You could also rotate around other fixed lines or points or whatever, but for us right now, we'll start off with the X and Y axis. So that distance I'm going to call R because I know that all the formulas for circles have the radius in them, or the diameter, which is, you know, twice as big as the radius. Okay, so if I come over here, this is the shape I would have, and this right here is that disc that I sliced out, right? This is the disc. So I'm going to come over here, and I'm going to do my best to try to draw this disc. Okay, now again, I am really bad at drawing. Oh boy. So let's try to draw it again. Okay, and now I'm going to try to make it three-dimensional. It's not going to work, but I try it no matter what, anyway. So supposedly, this is supposed to make you believe that it is three-dimensional, okay? So this disc has some thickness to it, okay? Now the thickness it has comes from this. This has a thickness of delta x sub I. So remember, whenever we did the Riemann sum, we said that each rectangle has a thickness of delta x sub I. So we're going to use the same idea as that. So this disc will have a thickness of delta x sub I. It'll have a thickness of delta x sub I. And if I wanted to find the surface area of it, this would be area of x sub I. So whatever x that I'm on, I could find the area of it. Let me write this a little better. So this distance from here to here is r, and this is going to have an area of ax sub I, okay? So if I wanted to find the volume of this disk, I could say V equals A times x sub I, because you guys know the formula for the volume of a cylinder, and this is technically a very, very short cylinder, is ax sub I times the height or the thickness, in this case, is delta x sub I, okay? Now, technically, we know that the area of a circle has the formula pi r squared delta x sub I. So all I did was I replaced this guy with pi r squared because I know area is worth pi r squared, okay? Now, here's the thing. What is r? Okay, well, r in this problem is this distance, right? We said it is, we said it is this distance here, right? This is my r. That's my distance, my radius. Oops, that's my r, right? So that distance right there, we could very easily calculate that by just finding the height of the function at that point. What if I drew another rectangle right here? Well, then the height would be f of x. If I drew one here, the height would be f of x. If I drew one here, the height would be f of x. So the heights of all of these rectangles would be f of x. That means the r is equal to f of x. So we can now come over here and we can keep going. We say v is equal to the summation, or I should say, v, you know what, let's do one more step. Let's say v equals pi times f of x quantity squared delta x sub I, okay? That's how we could write our volume. But that would just be of one disk. What if I wanted to do a whole bunch of disks, okay? So then we could say that the volume is approximately the summation of a whole bunch of disks Okay, so we go from I equals 1 to n. But this again is an approximation because we still have a set number of disks. We can't cover every little nook and cranny. There'll be some little curve. You know, what's the only way we can be exact? Well, you guys remember that when we wanted to be exact, we had to bring in the limit. We had to say the limit of the Riemann sum at infinity . So I'm going to write out this. Okay, so v equals the limit as n approaches infinity of I equals 1, the sum of pi times f of x squared delta x sub I. But then we remember, or you guys should remember, that that was the definition in terms of the limit of the Riemann sum was the same as the definite integral. So we can now say that v is equal to the definite integral from a to b of pi times f of x quantity squared dx, okay? So we took the limit of the Riemann sum, I think it was way back in 5.1 or 5.2, to find the definite integral. So now we're gonna take the same situation of taking an infinite amount of these disks. Remember, 20 disks would be pretty close, but it wouldn't be perfect. 50 disks would be close, but it wouldn't be perfect. The only way we could get the exact area and no longer be approximating is we have to take and approach an infinite amount of disks, okay? And so this will be our formula that we're going to work with, okay? So let's try to practice a problem, and I'll show you guys that it's not so bad. So find the volume. So notice something also to note is this is technically pi r squared, right? So we're integrating area and getting volume. That is an application of integration. Integration can take area and turn it into volume if you set it up correctly. So find the volume of the solid obtained when rotating the region bounded by y equals square root of x, the x-axis, and x equals 4 around the x-axis. Okay, so they're telling us how they want us to rotate it. So let's just draw a quick sketch, and this was what I expect to see on all of your exams, is a quick sketch. Okay, so I'm going to draw this little square root of x function. You guys know it's something like this, right? And then I'm going to cut it with the line x equals 4. So let's say that's like right here. Oops. So let's cut it right there. You know what, that's not a good color to use. Let's use this one. This is x equals 4 right here. Oops. And then this is y equals square root of x, or f of x. And then we have to find the area in between them. This is kind of a 6.1 question starting right here. This is like 6.1, okay? So it looks like we're going to be integrating from 0 to 4, right, of dx, because right here is where the graph intersects with the curve and the x-axis, okay, and here, and that stops at 4. So we're going to draw our rectangle. Let's just estimate it. Let's just make one up right here. Let's just say right there. So note, always draw your rectangle perpendicular to the x-axis. Or I'm sorry, perpendicular to the axis of rotation. Sorry guys, sometimes I'm thinking about something else in my head when I'm writing this. The axis of rotation. So whatever axis you're rotating around, when you're using the disc or washer method, you draw your rectangle perpendicular to that, okay? So I drew, my axis of rotation is the x-axis, so I drew my rectangle right here, perpendicular to it. Okay, and remember, we're going to spin this now, right? So we're going to get like a dome, basically, okay? And we need to know the r. Well, we know that r is worth f of x, so this will be pi r squared dx, right? But we need to substitute it in terms of x. So this will become pi times r, which is square root of x squared dx, but that's actually just... Now I'm writing way more steps maybe than you guys need. Some of you may already see this, but that's just the integral of x. Well, you guys all know this integral is pi times x squared over 2 from 0 to 4. So this will become what, 16 over 2. So this will become 8 pi minus 0, which is 8 pi. And we have our answer. Look how easy that integral was. Now again, these are the integrals you're hoping to get. These are the easiest integrals you'll ever see in your life, right? There's nothing better than this integral, okay? But the setup for it, where it came from, the slicing it up and rotating it and taking this disc and finding the area of one disc and then taking the thickness of that disc and calculating that little volume and then, you know, adding up a near infinite amount of them, that's complicated, okay? But the actual calculations themselves, not so bad. So let's try another one. So find the volume of the solid obtained when rotating the region bounded by y equals x, oops, just 2 this time, and y equals x squared about the x-axis, okay? So we're going to draw a picture again. Okay, so we have the line y equals x, just like that. And then we have a parabola, but we only have the parabola. Well, I guess we have the whole parabola, but you know that the only part of the parabola that's going to intersect. All right, so we could, ooh, that's so terrible. You guys get the idea, right? And then that, I guess, is a little better. Okay, but the only area that, or the only slice that we have is that right there. So that's our volume, or I'm sorry, that's our area, and then we're going to spin it around the x-axis. So then we're going to get this other shape down here. Right, and then we're going to have that. Okay, and then we're missing some inner portion. So in reality, this would be one of my rectangles, right? I'm perpendicular to the axis of rotation. But then isn't there like another one right here? I got to worry about two curves now. So what you do is you take the furthest from the axis of rotation and you call that your big R. So in this problem, big R equals y, which equals x, right? So this is it. And then little r will equal y, which will equal x squared, the parabola. So the parabola is the smaller one, okay? So what we're going to do is we're going to do two separate integrals. We're going to integrate. You guys can do inspection. I think you can find that this intersection point right here is from 0 to 1, okay? The x coordinate is 1, okay? And we're going to write pi times the big volume. So what I'm basically going to do is I'm basically going to find this volume here of the whole shape, right? So I'm going to find the volume of the whole shape, and then I'm going to subtract off this little missing volume right here, right? So that missing piece in the middle, okay? So I'm going to take the full volume, which would be the line y equals x. So this would be x squared dx, right? And I'm going to minus the other volume, which is from 0 to 1 of, oops, pi times r, little r squared, which would be x squared dx. So what I'm doing is I'm finding two separate volumes and then subtracting them. So if you think about it, I'm making this shape right here. If I took this slice right here that I'm making, if I took that disc, it would no longer be a disc, right? It would be this shape, but it would be hollow on the inside. And from here to here, that would be big R. And then from here to here, that would be little r, okay? So that's what I'm doing. And then I'm taking the volume based on the area in between, right? So that disc will have a certain height. We'll have a certain portion of it. So imagine if you had to find just the surface area of this donut shape, okay? Well, you would take the full circle minus the little circle, and the leftovers would be that little ring. Well, that's what the washer method is. The washer method subtracts the disk method, okay? So you use two disk methods and subtract. So this is what you end up with. Oops. You end up from 0 to 1 of pi x squared minus pi x to the 4th dx. So I can factor out my pi, and this will become x squared minus x to the 4th dx. Okay. And this is volume equals volume equals volume equals, okay? So then we're going to have volume equals pi. And now look at this integration. X cubed over 3 minus x to the 5th over 5 from 0 to 1. It doesn't get any better than that. That's the best. So now we have pi times 1/3 minus 1/5. And then we don't worry about the other one because it's just going to be 0, right? So this would be what? 5/15 minus 3/15, so 2 pi over 15. Pretty sure. Double check my math on that, but I'm pretty sure that's it. Okay. So those are basically the disk method and the washer method, but all the washer method is the disk method twice. Okay. So you have to find the furthest, and the way you can always calculate, like I said, big R, is the furthest from the axis of rotation. That's your big R. So whichever graph is furthest from the axis of rotation, that's big R, okay? So now let's look at another one. Let's do, oh geez, let's say set up, or let's say find the volume of the solid obtained when the region bounded by, and again, you guys know you'll always get positive numbers because whenever you start talking about the region bounded by two curves, it's always got to be positive, like in 6.1. I think in some of the homework from 5.5 or 5.3, they also tried to sneak that past you. They said the region bounded by, and in a way, they're just saying do absolute values because you always want positives. Whenever you're trying to find the region bounded by two curves, it must always be a positive number because it's an area. If you're just doing a plain old definite integral, then the definite integral is defined as area above the x-axis is positive and area below the x-axis is negative, okay? But if you're saying the area bounded by two curves, then you have to start thinking absolute value and everything's a positive area, okay? So it says find the volume of the solid obtained when the region bounded by x equals 2 over y, the y-axis, y equals 1, y equals 4, is rotated about the y-axis. So this is trying to flip it on you a little bit. We have to be a little more careful now. Okay, so x equals 2 over y. So that would be y equals 2 over x. You would get a curve something like this. It's a diagonal looking parabola or hyperbola. Okay. So we have this situation, and I'll just continue it on, but that's basically it. Okay. And now the big difference this time, you guys, is that we are, okay, so we're cutting it off right here. Here's a height of 4. And then they also said a height of 1. So there's a height of 1. We're finding this area here. They said use the y-axis as kind of the other portion that you stop shading, right? Okay, so that's basically the area we're looking at, okay? And the big twist is that we're rotating it around the y-axis, right? We're spinning it around the y-axis. So that means we're going to have this shape over here also. All right. So technically we have this solid. I guess it kind of looks like a lampshade a little bit, something like that. And we have this solid. And notice there's no hole in the middle. This isn't like the washer method. This is just pure disk. There's not a second curve that we have to subtract and we have a missing gap in the middle. It's nothing like that, okay? But the big difference is we are rotating around the y-axis, so we have to draw a rectangle right here, right? Perpendicular to the axis of rotation. So that means our big R will equal how far away we are from the y-axis, so that would be an x value. Notice that this distance from here to here would be an x value, not a y value, okay? So this is my big R. So this time big R is the x value. So that means that we're going to integrate from 1 to 4 using limits of integration for the y coordinate. So whenever you're doing the disk or washer, if you're working with dx, then you need to use x coordinates. If you're working with dy, you need to use y coordinates. So we're going to go from 1 to 4 times pi times r squared dy. But we know that this is from 1 to 4. Oh, you know, I can take the pi out right now. Pi integral 1 to 4. Now r is x, but x is 2 over y squared dy. Well, that's not so bad. So we're going to say volume equals the integral of pi times 4 y to the negative 2, right? Because this is actually 4 over y squared dy. but then volume equals pi, and this would become 4 pi times y to the negative 1 divided by negative 1 from 1 to 4. So this becomes negative 4 pi 1 over 4 minus 1. So let's see here. This would become, oops, you know what, let's just go over here. Negative 4 pi times, what was that, negative 3/4? And the 4's cancel, and the negatives cancel or become positive, I should say, and we're left with 3 pi as our volume. So we have a volume of 3 pi, okay? So for the most part, that's how you could do a problem like this, okay? You could do the washer method. Maybe I'll do 1 or 2 more. I'll do 1 more like this. So find the volume of the solid obtained when find the volume of the solid obtained by rotating the region bounded by y equals x squared and y equals 2x about the y-axis once again. Okay, so a very similar problem to something we've already worked with. Let's take our sketch once again, and again, I expect to see a sketch on every single one of your exams when you turn this in. For these type of problems, for 6.1 and 6.2, I should see sketches for every single problem. So 2x would be rise 2, run 1, so this will be a little bit steeper. Okay, so we have that. And then we have the parabola x squared again. So we're intersect up here a little bit higher, okay? Technically, I know it comes over there, but that part doesn't matter because it's not going to intersect, so I'm not too stressed about it. Okay, so we have our little slice right here, right? And now we're going to spin this around which axis? So I got to erase that because we're going to spin this around the y-axis again. So when we're spinning it around the y-axis, okay, for the disc washer method, that means we have to draw our rectangle perpendicular to that. But then remember, we're also going to have a little rectangle right here as well. That's little r. So that's little r. That's big R. Oops, big R. Okay. So I'm going to try to integrate. So as it turns out, this intersection point right here, so our y value, if you guys go by inspection, you could say that x squared equals 2x. You could say x squared minus 2x equals 0. So you could say x and x minus 2 equals 0. So you could say x equals 0 and x equals 2. But those are x coordinates. If I want to find the y coordinates, I got to plug those in. So when x equals 0, y equals 0. So when x equals 2, y equals 4. So we know that we're integrating from 0 to 4. Okay? So that's how we found our limits of integration. I don't know if I showed that in the last one, but you can also do it on your calculator and find it by inspection. So now we have to do which curve is furthest from the x-axis. Because remember, we're creating this shape over here. So we're creating this little solid. It's like some kind of cup or a bowl or something like that, right? Because we're spinning it. So it's going to be hollow a little bit, but it'll still have some thickness to it. It still has some volume. So we have to find that volume. So we take the biggest curve, which would be the one furthest from the axis of rotation. So that would be the parabola x squared. I'm going to just pull the pi out because I've been doing it so often. So squared minus pi times the other one, but I'm going to pull that pi out. So there's a pi. That's why I have the pi in front. You know what? I better not confuse it. I better put the pi here and the pi here. And then now the little r is 2x. dy. Okay, now here's the problem. Those are x's, and they asked me to do it around the y-axis. So you could try to use the shell method or something like that, but I haven't taught you the shell method yet. So this will not work with the washer method. So what we need to do is set it up differently for the washer method. So from 0 to 4. Remember, we're working with dy, you guys, so that means the variables have to be dy, okay? Or in terms of y. So then we have to solve x squared for x so we can substitute in y. So we're going to square root both sides, okay? So that technically means that big R is worth the square root of y squared, okay? Minus, now I'm looking at, so I'm looking back up here and I'm solving for x in both of these. This one will be y over 2 squared times pi dy. Let me clean this up a little. Okay, and then all of this dy. All right, so now I'm going to factor out the pi like I wanted to do earlier. So this will be volume equals the integral from 0 to 4 of y minus y squared over 4 dy. Now look at that integral. It looks worse than it is. It's actually a really nice integral. When you look above, it looks bad, but this is actually just y squared over 2 minus y cubed over 12 from 0 to 4. So v is equal to pi times, what is this, 8 minus, what is that, 64 over 12? Minus 0, right? Because we plug 0 in, so let me see. 16 over 2 would be 8. 64 over 12, we could cancel and we could cancel. And this would be divided by 4 would be 16 over 3. So v equals pi times, and I'll just do on my calculator, 8 minus 16 divided by 3. So I get 8/3. So my volume is 8 pi over 3. Okay, so that's how you can do some problems with the disc washer method when you're rotating around the y-axis. So there's one more I want to do, and then I think I'll call it a day on this video. So let's look at a similar problem. It says find the volume of the solid obtained when the region bounded by y equals x squared and y equals 2x. So we'll do the same exact problem, is rotated about the line x equals -1. So that's the twist. We're not rotating around the x or the y axis. We are now going to rotate it around the line, the vertical line y or x equals -1. So let's draw a quick sketch. So here's -1, right? Here's +1, okay? Now we know, you know what, I think I need to draw this a little different. I need some more room. I'm gonna draw it over here this time. So let's say that's -1, let's say that's +1, okay? Now we know kind of what this shape already looks like. We know that we're gonna get something like this. Oops, that's really bad. All right. So that's the region right there. That's the region that's bounded. Okay, so it's the same as this. I'm just drawing it. I'm doing my best to draw it, guys, but it's the same drawing, okay? But instead of rotating it around the y-axis, we're gonna rotate it around this line right here. So now we're rotating it around there. So remember, you always draw your rectangle from the axis of rotation. Okay, and then our little rectangle, right? So we have little r, and we have big R. Oops, I always do that, big R, okay? So here's the catch. What is this distance right here now? You see this right here? What is this distance? Oops, that's bad. So I need to know right here. I need to know this big R distance. How far is that? Well, it's the same as it used to be, but isn't it now one further? So in the previous problem, we said that big R was the square root of y, okay? So in this problem, it's going to be big R equals the square root of y plus 1, because it's one further than it used to be. And then little r, we said in the previous problem, was y over 2, right? Little r was y over 2, if you look right here, y over 2. But now it's one further than it used to be, so we're going to say plus 1. Because the distance is the radius, right? How far you had to go to draw that rectangle. That's why you draw it. That's why you take these sketches, to remind you of all this. So now, when we integrate, we're going to say volume equals the integral. So we're still going to be going, you know, I'm going to pull the pi out. I'm actually going to do it this time from 0 to 4. Now we have to do square root of y plus 1 squared minus, let's see here, 1 plus y over 2, or y plus 2, y over 2 plus 1 squared dy. Okay, so let's do some cleanup. So this would be y plus 2 square roots of y plus 1 minus y squared over 4 plus, let me see here, this would be y plus 1, I believe, dy. Yeah, because when you FOIL, when you do a little scratch work over here of y over 2 plus 1 times y over 2 plus 1. When you guys FOIL this out, if you're wondering where I got it from, this would be y squared over 4 plus y over 2 plus y over 2 plus 1. Well, that's y squared over 4 plus 2y over 2 plus 1, but the 2's cancel. So that's where I got this y right there. So now this y will cancel this y because of the minus sign, okay? So then we're going to have volume equals pi times the integral from 0 to 4 of 2 square roots of y. This one will cancel, oops. This one will cancel this one. And we're left with negative y squared over 4 dy. So I believe that's that. So now we can integrate. So this would be 2y to the 3 halves over 3 halves minus y cubed over 12 from 0 to 4. So when you plug 4 into the 3 halves power, you get 4, square rooted is 2, so that'd be 8, so that'd be 16. That'd be 32 thirds, I believe, minus 64 over 12 minus 0, right? Because the other guy. And then this will become 16 thirds. 16 pi over 3. Let me do some of that math. Let me double check my 2y to the 3 halves. So 2 times 4 to the 3 divided by 2 divided by, parentheses 3 divided by 2. And I said that was 32 over 3, that's right. Yep, so that's good. So that should be our final answer. So this is how you can rotate around something other than the X or the Y axis. I'm gonna go ahead and end the video with that. Please let me know if you have any questions about this. We're starting to get to the end. This may be the last section we have time to put on this exam. So please make sure you go over this. All right, you guys, that's gonna do it for this video.